Welcome everyone to this tutorial for the overlay on low-dimensional structures. In the previous video we saw an example of simple overlay with the Mona Lisa or Nano Lisa. So we pattern a frame and then we scan it and place our design inside it in exactly the position that we wanted to keep. So now I would like to show you the overlay, an example of overlay on low dimensional structures, and following this tutorial you should be able to effectively do your overlay with your NanoFraser. First of all, which kind of samples do we have? We have what we call a training sample. Some of our NanoFraser users should have this sample. It's a sample with the silicon substrate. We evaporated these structures. The structures are made of chromium and they're around 30 nanometers of about 30 nanometers height. So it's a sample that can be used for training, indeed. So we have this small structure are meant to simulate 2D materials flake. We also have some other areas where we have fake nanowires and similar stuff, or any other kind of structures like this structure, which can be used for automated overlay or some other type of training with the NanoFraser. So let's say the goal of this video now is that of contacting, for example, this small flake to an electrode. So here we have this big electrode, our flake. And so what's a typical approach? Similarly to the previous video with a Mona Lisa inside the frame, we want to scan our flake or part of it. So again, I have to move to the read arbitrary function. I can select the whole flake. I allow the stage movement, and in around 54 seconds we should be able to scan our flake. The biggest difference with the previous tutorial is that now we're going to use the export in KLayout function, and we see how to integrate KLayout when with the NanoFraser software to have the very high precision overlay with low dimensional structures. So after we scan the surface, we see our nice flake. Fake flake. It's actually chromium, around 30 nanometers height. Let's not forget that with the NanoFraser we can pretty much scan all the 2D materials. Even monolayers of 2D materials can be seen using the NanoFraser. Most of nanowires and nanoparticles can be scanned as well. If you want more details regarding this, you can go into the information panel in our supporting documents in the recipe book, which is a very important document, and I again suggest you to have a read if possible. In chapter 2.3 in the spin coating we have a spin coating theory with some information about polymer flow on topographies. So we mention here the residual topography on different nanostructures, and this should give you an idea of what's detectable and not detectable by the NanoFraser. Usually structures like single-walled carbon nanotubes cannot be detected because they're too small. So now let's move back to our session. We've done the reading. We can remove the allow stage movement, and what we want to do is exporting this warm-up with these coordinates in KLayout. So we press this. Okay, so you see that now we have the view of the optical camera, and also we have the topography that we scanned, and we're using the coordinate systems of the warm-up of the nanofraser. So let's say we want to connect this flake. We can draw a polygon, for example. I can draw a connection here, here, and here. Okay, this is our contact line. Now we save the file and call it overlay 1, and we just put it in the desktop. Then we, if we want, we can also see what happens if we draw multiple layers. In this case, we only have one layer. With KLayout in general, we can also have multiple layers. Let's see, we want to draw a triangle here. This will be part of layer 2. When we import this on the nanofraser, we will see that there are 2 layers in the geometry tab. So it's also a good example for seeing this functionality. So now let's go back to the geometry. We want to open desktop, open overlay 1, and we see that we have 2 layers. The first layer is our contact line. The second layer is the triangle. For now, we can just pattern the contact line, but I just wanted to show you that if you have another layer, you can choose its depth and you can choose whether to select it or not. In this case, we're going to pattern, say at 40 nanometers. My best suggestion to you when doing overlay on pre-existing topographies is to pattern without a feedback, because usually the feedback struggles a little bit when patterning across this change in of the surface of the topography, height of topography. So here we are around 30 nanometer step. So it's a little bit harder for the feedback to follow this topography at the moment. So what we recommend to do is trying to do a test pattern somewhere. So in this case, when we're contacting over flakes or nanowires, we always do 2D lithographies. So we will find a good value for the force through the feedback, and then we will use this value of the force and with a specific value of temperature and forward height to pattern our structure. So in this case we put 40 nanometers depth, but we don't really care that much. So we split the geometry. We see that it's being split in multiple fields. Actually here we can resize them so that we have just a couple of fields. We can also decide to change the overlap. When we split any geometry, we have to remember that we can either make a standard stitching or an active fill stitching. Now we can just do a standard stitching and we can increase the overlap a little bit. It's not really required to do an active fill stitching if we don't really need a high resolution patterning, like in this case, so a standard stitching should be enough. Once we're happy with our splitting, we can import our layout. Actually, I forgot an important thing. Since we're using the same coordinate system in KLayout of the one that we're using in the warm-up of the NanoFraser, we have to check this warm-up position from file coordinates. So that this will place the design exactly. Sorry, I got lost. It's easy to get lost in this case. But anyway, this will place design exactly where we want it on top of our flakes. So we add it as a new design and this position will actually be correct. We can also see the difference in position between the two designs. So let's go to the right layout. We see we import the layout without the right coordinate system. Okay, we actually have some problems with this field. I'll try to fix them. It's probably related to the scan region, so we may have to increase the pixel time to maybe 40. Okay, so we had a scan region that was too large for that pixel size. So in this case, you see that let's unselect this field. This layout TSPL2 has the exact position that we had here. So very, very powerful tool. In this case, we're patterning both this contact line and this triangle, and they're going to be patterned at this, using the same disabled feedback mode. So I did a test of a previous pattern, and I found that a good conditions for patterning is 1000 Celsius, 5 volt, and 250 nanometers. So I will just disable the feedback now and run the writing. So yeah, let's just start it. It's gonna take around 7 minutes. So let's see how it goes. Also, as mentioned earlier in the video at the other not low dimension, sorry, but the overlay with the Mona Lisa, we should unselect the allow stage movement when we want to place with the highest precision our layouts on top of the existing structures. Here it's not very crucial because we don't have a very high resolution alignment, but it's something that we need to keep in mind in case you want to have to avoid the error in alignment of fields that introduced with moving with the coarse stage, and we're talking about 100 nanometers pretty much, and it's an error that's not always constant, so we cannot have a fixed number for that. It's quite hard to define, so just to know kind of errors that you can introduce and how you can avoid it. So unselecting this allow stage movement. In case we want to do an active field stitching, now we're doing a standard field stitching. We can also check this active field stitching, and this will work in a way that we will write field number 1, then we will read the margin of field 1 and then align field 2 to this to field number 1. While with the standard stitching process, we will write field 1, then we will move with the course stage, and then we will write field 2 without any reading and any alignment. This procedure is faster, but also is less precise because it has the errors that are introduced with the motion of the course stage. So we see now we're patterning quite okay. We have a depth of around 20-30 nanometers. So actually a little bit more. Here we have a depth of around 40. Here we have a depth of around 30, 40-ish. And again, patterning with feedback disabled is quite helpful in this case. One thing that's important to remember is also that when we do overlay, typically we have a bilayer lift-off process. So we're talking about most of the cases about a 2D lithography. So that's already one thing to keep in mind. Second thing is that since we're talking about a bilayer lift-off process, usually we have a stack that has either PMMA-MA or PMGI with on top a layer of PPA. And usually in order to have a successful bilayer lift-off process and a successful lift-off, we need to write at a depth that's larger than the PPA layer thickness. So let's say we have 60 nanometers of PMMA-MA and 20 nanometers of PPA. In this case, we would like to pattern at depth of around 23, 25 nanometers to make sure to open the PPA mask so that the development process will be effective. So I will not dive much more in detail regarding the bilayer lift-off process, but this is just something that I wanted to mention. And if you want to find more information regarding the bilayer lift-off process, you can always, and I again really recommend you to read if you haven't done so, you can always read the recipe book. We have the bilayer lift-off chapter. So exactly here. It's actually a sub-chapter 3.1. It's 4-5 pages, very dense with information, mostly experimentally, but I think they're very useful for you to understand better what you're supposed to do based on our experience of a successful bilayer lift-off process, with many suggestions, both in experimental part and also in the design part of your stack. So have a read of this, it's very helpful. Also, you can find more information regarding the bilayer lift-off process in the application notes. So in the meantime, let's check our our patterning. Here we are patterning on top of the contact pad, and we have some artifacts because of the flattening issues. So we are flattening on the right, but so where the Nanophraser software thinks that the right part, the right side of the image is at the same height, but of course it's not, because this is around 30 nanometers and the bottom part is at 0. So we see that this image is as kind of an artifact, which is from this way up. It's not really the real topography. It's also something to keep in mind. If we're patterning without a feedback, it doesn't really matter, because we will always apply that force and the temperature without any change. But if you use a feedback, it's something that's good to keep in mind. And just to show you that what I'm saying is actually true, let's do a quick reading process. We can also see that we have patterned quite well. So if we unselect this, we can also optically see that we have patterned our contact line on top of the contact pad. Let's select again this one. So let's just do a reading, arbitrary, of this area. And we see that now the scan direction goes like this, so it will be still problematic if we flatten on the right. So what we can do is rotating our design by 90, for example. And in this case, we will go from bottom to top. And we can select a 0 reference margin on the left. So this is now the left, this is the right, because we changed the fast scan direction. So let's go to the CLL patterning parameters and we select the reference margin on the left. Now we can read again. So now we can clearly see this interface, which gives us a better idea of the real topography that we now have on our surface. You can also see that we pattern in this area around 20 nanometers deep. Then here, when we are just on PPA, we're going a little bit deeper. And again here. So this is more a realistic topography, and of course you can do a proper flattening either with the Nanophraser software or with other software. We can also see the overlap between the two fields. In this case of making contact lines with the Nanophraser, it's not really a problem if we have an overlap that causes a deeper, a larger depth, because for a successful bilayer liftoff, we want to at least open the PPA mask. It's going to be problematic if we don't pattern deep enough, but deeper is usually not a problem. So yeah, this is already quite a long video for our standards. I hope it was quite useful. I I think it's quite a common application of the nanofraser, so it's important that we have some materials that explains you how to perform a overlay on low-dimensional structures. And yeah, I hope this was clear, and good luck for your patterns and overlay on low-dimensional structures with the nanofraser.